48th AMATYC Annual Conference. Thank you for being here. It means a lot to have presenters who are willing to give of their knowledge and time. And it means a lot to the presenters to have colleagues who are interested in what they have to say and what they have to share. So thank you to all of you. On Thursday morning, we heard from two of our corporate sponsors. This morning, we'd like to invite Catherine Bates to the stage. She is from Wiley, and Wiley sponsored our breakfast this morning. So we would like to give her a moment.
Very kind of you. Thank you, everyone. Good morning. I just want to say on behalf of Wiley, thank you for doing the work that you do. I think as a person, for me, one of the highest compliments I can give is that a person is a teacher. And it's even, that's who you are. So yeah, I really appreciate the work that you do day in and day out. And if you'll never get enough thanks, so I'll say to you, thank you. Wiley is happy to be part of your world and to hopefully be a good partner in your success. So thanks for the opportunity. I hope this has been a great meeting for you, and I hope we all get to gather again together next year to do a good job with teaching and helping students. So thank you.
Thank you, Catherine. And we do appreciate the sponsorship from Wiley. It helps us to gather together and we enjoy breakfast. Okay, I want to introduce you to the 2022-2023 Executive Board. We've got myself, Laura Watkins, as president. George Holbert is our president-elect, and Kate Kozak is our past president. We've got Barbara Steinhurst as treasurer and Nancy Rivers as secretary. AJ Stehelic, I always want to say it's not, it's Stehelic. Dennis Ebersol, Northeast VP and Mid-Atlantic VP. Alvina Atkinson, Southeast VP, and Brandon Bartley as Midwest VP. Dale Johansson as Central VP. Shannon Ruth as Southwest VP. Sarah Pauley, Northwest VP. And Eddie Churchian as West VP. Then we've got the hold on, just one more minute. And then we've got the AMATYC office, our executive director, Ann Dudley. And then Beverly Vance, Christy Hunsucker, and Christine Schott, and Angela Poulin. I could not do what I do trying to lead this organization without these wonderful people to help. So please give them all a round of applause. All right, so moving on. Can I have the affiliate presidents stand, please? There's a few in the room. Our affiliates are how we connect to the various areas of the nation. And you do yeoman's work. It's tremendous work that you do trying to help the teaching and learning of math in the first 2 years of college in your local environments. And it is much appreciated what you do in your local communities. Can I have the past presidents stand? We have a few. They're down here up front. We've got 4 in the room. These people have dedicated a good portion of their life trying to advance the teaching and learning of mathematics in the first 2 years of college, and AMATYC really appreciates your efforts in that behalf. Next, okay, so we would not be enjoying what we're enjoying this week if it were not for the conference committee. We've got Turi Susky as conference coordinator, Natalie Vega Rhodes, she assists Turi, and she is the Hoover guru, I've come to understand. Michael Pemberton is the program coordinator, and Julie Gunkelman is his assistant. And then we have the committee, Jose Maria Menendez, Julie Hansen, Rochelle Beatty, Mary Beth Sy, and Pat Riley. So can we give them, please, a very warm thank you. Hours and hours of work. And I will tell you, I was emailing Tori at 11:30 last night, and we were still doing some touch-ups, and then again at 6 o'clock this morning. So I know they're running on fumes about now, because I'm running on fumes about now. But so if you see them, please give them a personal thank you. Okay. So I'm not, yeah, sorry. I forgot about this slide, sorry. Yeah, Crystal Wiggins, advertising, thank you. And Todd, he's in charge of the exhibit halls. And Sarah Miller, I haven't seen her, but if you ever have to come to a conference and you want to share a room, she's our roommate coordinator. She will try and pair you up with someone. Okay, here we go, sorry. Okay. Sean Saunders, can you come on down? Okay, well, Sean has been working with his local committee for a couple of years now, preparing for this conference. He's been helpful in finding local speakers. We've got Sunil Singh and Stan Yoshinobu, great speakers. He's written multiple articles for the AMATYC News. He's helped with logistics. Who went to the Winter Village last night? Did anyone here go? Was it good experience? Okay, good. And tomorrow it's?
Today it's the aquarium, and tomorrow it's the Science Center.
Today aquarium, tomorrow Science Center. I hope you get a chance to go out and see a little bit of Toronto. He's just done so very much to help this be a successful conference. So on behalf of AMATYC, I would like to thank you for all of your work as the 2022 Local Events Coordinator. And we do have a plaque for you. And our photographer, he's coming.
Oh, yes.
Oh. Thank you. Okay, let's see where we're at here. So while Sean did lead the effort, he did not do it alone. And so we do want to thank the entire committee. Would the Local Events Committee please stand and be recognized? Okay, so next we have our Academic Network, or ANET chairs. We want to recognize them. Hopefully you've been able to connect with one of our ANETs. If not, on Thursday or Friday, maybe today. I know I'm headed to an ANET meeting a little later today. So we do want to recognize, oh my gosh. All right, I am so sorry. some of the names here are wrong. Okay. Anyway, so that's what happens sometimes. Okay. Yeah, Kim, I'm so sorry. And you're right over here. I saw you somewhere. She's right over there. She is. Kim, I'm so sorry. Kim Granger is developmental math. Okay, but you see I have her picture, right? All right. Jennifer Ackerman for ITL. We've kind of dropped the C. We're not sure what to do with the ITLC, the C in the ITLC, but Innovative Teaching and Learning. Ben Aschenbrenner with the Equity Group. Robert Capetta with Math Intensive. Natalia Pastragan with Mathematics and its Application for Careers. Rebecca Wong for Statistics. Christine Mirbaha for Placement and Assessment. Frank Marfai, Research and Mathematics Education for two-year colleges. Mark Coleman for Teacher Prep. Helen Byrne, Mathematics Pathways. Chris Ward, Division and Department Leadership. Barbara Letherer, International Mathematics. Patricia Barrientos, Adjunct Faculty Issues. I can spit that out. And Greg Foley for Mathematics for Liberal Arts. And then we do still have one subcommittee remaining. And we've got Rachel Saidi, who's with the Data Science Subcommittee. Could we please recognize these leaders and all of their efforts? Thank you so much for all that you do. All right, now we have our impact team. We've got Julie Phelps. She is the standards chair, and they have been doing a lot of work this year, working on updating our standards. Not just Julie, she's got a whole team. Evan Evans, of course, is helping with that effort. He is our digital products coordinator on My AMATYC. And then we have Karen Gaines, and she is the online community coordinator. She puts a lot, and when I say a lot, I mean a lot of time and effort into My AMATYC. So please head on over and take a look at what that has to offer. There's libraries and a conversation you can have there. But she puts a lot of effort into that, hopefully making it something that is a valuable resource to our members. Peter Georgakis is our legal advisor. Jonathan Weisbrod is our representative to Mu Alpha Theta. We've got Vicki Mayfield. She is our editing director. Megan Bright Goodwin, she's our grants coordinator. And currently, we've got Teaching for Prowess, and we've got Project Gains, which is an effort to reach out to graduate students and invite them into the profession. And there's a few more grants that are coming our way, so stay tuned. AMATYC Publications, we've got Jennifer Travis. She spends a lot of time helping to produce the AMATYC News, and she is the editor of that. Then we've got Ryan Pescosolito. I practiced that, and it didn't come out. Pescosolito, he's our website coordinator, and he does wonderful work. We've got Johanna Debrecht, who's the editor of the Mathematic Educator. George Alexander is the assistant editor. Keith Knabb is our production manager. It's a wonderful resource that we have our own referee journal, and they put a lot of time and effort into producing that for us. Professional development, we've got Banaz Rouhani, and she is the coordinator for professional development, and Mary Menard, who's our webinar coordinator. Again, they put a lot of time and effort into offering resources to the community outside of this amazing conference. So hopefully you start to look at AMATYC as a year-round resource, not just a conference. We've got the AMATYC Foundation Board. These are volunteers that work together. We meet monthly to discuss the foundation and how the foundation can further the work of AMATYC. We've got Fred Peskoff, Ernie Danforth, Cheryl Cleaves, Bill Stinken. Myself, I serve on the board, Kate Kozak, Barbara Steinhurst, and Sarah Polly. And of course, Ann Dudley, the executive director. So, yeah, that's good. Next, project access. Lisa Feynman is our current project access coordinator. Thank you, Lisa. Now, I'm going to, the next slide, you're not going to be able to read, and that's okay. You can find it in the AMATYC news. But I just wanted you to see that we're rebounding from the pandemic, right? We've got cohort 17, cohort 18 in the room. Will cohort 17 and cohort 18 please stand? Will any project access fellow in the room, stay standing, stay standing. Any project access fellow in the room, please stand. Thank you. Project access is an amazing professional development opportunity for faculty in the first 4 years of their first full-time appointment at a 2-year college. So please encourage any of your colleagues that fit that requirement to apply. If you pull aside any project access alum, you will probably hear how it was the best 1.5 to 2 years of their life. I don't know. That's maybe exaggerating a little bit, but it was an awesome experience. Okay. All right. Next, it's time for the Student Mathematics League. So we've got Matthew Pregel, he's the current coordinator. TJ Duda is the test developer. And Steve Blasberg is the Faculty Math League coordinator. I'm going to ask Matthew Pregel, Aaron Kelly, and Steve Blasberg to come and join me on the stand. So Aaron Kelly is a representative from Pearson who is kindly sponsoring the Glenn Smith Scholarship Award. Go ahead. There.
Hello everyone, my name is Matthew Pregel, and while I'm not trying to hype people up for the Faculty Math League competition, I also serve as the Student Math League coordinator for the contest. In the 2021 academic year, we brought our contest back, and it's my pleasure to announce the top 3 teams from that competition. These teams all received their plaques at the lunch yesterday, but I wanted to recognize them. In 3rd place was Tarrant County College. In 2nd place was College of the Canyons. And in 1st place was Pasadena City College. Congratulations. Next up, I'd like to introduce Aaron to award the Top Student Award, our Charles Miller Scholarship Award. Would the moderator from Pasadena City College, Jude Socrates, please come up?
Good morning. Thank you for having me. I speak for all of my Pearson colleagues when I say that we are thrilled to be part of the AMATYC community, and we are grateful to be able to support future mathletes like Jun Yang Zhu. I also practiced that and didn't get it right. As a future mathlete. And thank you all for spending time with us this week, and we look forward to seeing you in Omaha. And I'm going to hand this to
The moderator.
the moderator.
Thank you so much. He'll arrange you.
I'm Steve Blasberg. I am the coordinator of the Steve Blasberg Faculty Math League contest. It's always a pleasure to be able to say that without having to say it's memorial. So I have the results of this year's Faculty Math League contest, both the individual and the team competition. So the individual top 3 finishers this year are in 3rd place with a score of 23 was Aisha Arroyo from Middlesex Community College in Massachusetts. And for the first time in my memory, we have a tie for first place between Spencer Bartholomew from Salt Lake College, City College, and someone who you have already seen at the podium, and that is Sean Sanders. Normally at this point we would present a gift certificate for the winner, but I only have one of them, so we will make arrangements to duplicate that later on. See me after the breakfast. As far as the team competition, it was no contest this year. As you can imagine, Sean Sanders and Aisha Arroyo are both from the Northeast. So it was not a question that the Northeast won the team competition, and I believe they're holding onto the trophy. Is that right? Yes. Thanks.
Congratulations, and thank you to everyone who went and competed. That sounds like it was a wonderful experience. Okay, so we do have another competition, the Student Research League. Karen Gaines, will you join me on the stand? Vinod Chalamusu is the coordinator for the competition, but he was unable to travel to be with us. So Karen Gaines has consented to come on up and make the award.
Thanks, Laura. This is the 5th year of the Student Research League competition. It's basically a question that pops up in the springtime that requires some research, problem solving, mathematical modeling, and then creating a thesis defense. The topics that have been covered the previous years have included what's the safest place to live in America according to Mother Nature's wrath? What's the best energy source for your personal home? How to get rid of student debt, that was a popular one, and feeding the crews on their missions to Mars. This year's was entitled Let's Drive the Future. The students were asked to take a vehicle, whether it was a personal one or a delivery vehicle, and determine by cost-benefit analysis if an electric version is the better way to go. So I would like to present the first place. Somewhere. There you go. To Midland College, the students are Parker 2, Eduardo Ornelas Cabello, and Ornaldo Montanez, with the faculty mentor Jamie Neasley. So if they would come up. That light's
I know,
really
Brooke's lights are horrible. Oh, they're here. Wow. Okay, he's gonna try and do a group.
get them.
Congratulations, that's wonderful.
Oh, wait.
Yep, go ahead.
enter your teams for next year's competition. The information will be up in January, and if you don't have a team, you can also be an evaluator. We need those.
And just so you know, the prizes associated, the first place team gets a $1,000 scholarship, up to $3,000 for the team. The second place winners get a $500 scholarship, up to $1,500, and the third place team gets a $250 scholarship, up to $750 for the team. So consider working with some students and having them compete. There is scholarship money in the offing. Okay, well, now it's time for almost the keynote. One more thing to announce. Will George Alexander please join me on the stage? I don't know if how many of you know George or what he does for the organization. I suspect Wisconsin does. So George has performed important work for AMATYC, and it's very behind the scenes. He has worked on the Mathematic Educator, near as I can tell, since 2012, in a variety of roles. He has been just a steady voice in making sure that we are able to offer our refereed publication. If you're an AMATYC member, you receive a copy of each issue, and currently he is the assistant editor for the journal. But like I said, he's had many roles, and he's kept it. He's been a common voice over the years with the journal. So we have this wonderful journal in part because of George and some of his colleagues. So George said it's not all me, and so he does want to take a minute or so to recognize a few people.
Thank you, Laura. It has been a really great pleasure working with the journal all these years, and I'm not going anywhere yet, so this is not a farewell. I have great staff to work with, both Keith and Johanna as part of that team, but we gave a presentation Thursday, and it took 4 slides to recognize all the people that have a hand in this journal, from reviewers to the editorial panel to proofreaders, and it's just an enormous list of people that are involved in this, and great volunteers. All of you make me look good, and thank you very much.
Thank you. Thank you, George. And next time you pick up your Mathematic Educator and you open that front matter, you'll find his name there. Okay, it's time for our keynote. I lost my clicker. I set it down in the back. Okay, our keynote speaker this morning is Ben Orlin. You may recognize him as the author of Math with Bad Drawings. He is a best-selling author, he does love math, and he is teaching math at St. Paul College, if I remember correctly. He says he cannot draw, although he's got books that show he can. I don't know. He received a bachelor's degree in mathematics and psychology from Yale, and has taught mathematics to students every age from 11 to 18 on a variety of topics, from arithmetic to differential equations, with every level of competence from, wow, that was a fiasco, to, hey, that actually went well. He's written 3 books and has a blog, Math with Bad Drawings, that was launched in 2013. And quickly drew millions of views thanks to cartoons such as Why Not Trust Statistics and Math Experts Split the Check. as well as essays on education like what it feels like to be bad at math and the state of being stuck. So his work has appeared in the Atlantic, the LA Times, the Chicago Tribune, and a number of other venues. He also has contributed cartoons to Eureka Math. It is the most widely distributed secondary math curriculum in the US. He's a resident of St. Paul, Minnesota, and this is his first time in Toronto, and he would like to eat all things maple. So Ben, please come join me on the stand.
Great, thanks so much. All right, hey everybody. It's really great to see you this morning. Thanks for being up early on a Saturday. And I want to express my gratitude, but also I think my awe and my admiration to all the organizers, all the AMATYC team, the leadership, everyone who organizes this conference. My event organizing has extended to like a 3-year-old's birthday party, or like having some friends over for dinner. And like I'm always like, I can't do this alone. This is huge. This is too big a task for me. So something like this, where you've got 700 people converging on a foreign city, is an incredible achievement. I think how fun and smooth and successful this conference has been. So thank you to all the leadership. If you want to applaud them again, you know. They've gotten a lot of applause, but there's no limit to the amount of applause they deserve. Yeah, so anyway, thank you for having me. I think of myself as a teacher, although I've spent the last 5 years as a full-time writer. I've been writing these books. So I may just show you real quick my 3 books. I think of these as my babies, so I like showing them off every chance I get. So the first one I wrote was called Math with Bad Drawings. And I think of this one as, first of all, it's very generous that people always say the drawings are not that bad. They truly are. I mean, I don't know, I've got some students in the stats class I'm teaching right now where I've told them that they need to give me instructions. They're both great artists, siblings. So what they do is they draw little instructions in the margins of their quizzes, teaching me how to draw things. Like, so I know how to draw a hedgehog a little better now than I did a few weeks ago. So you know, I'm growing, I'm learning. That's the idea with Math with Bad Drawings, is we're all growing and learning, me as an artist. Been working on it for a decade. I've got decades more of growth to go. Anyway, so the first book, Math with Bad Drawings, basically a big party for mathematics. It's about lots of applications of mathematics. So, you know, why triangles show up so often in architecture, Conway's Game of Life as kind of a model for complexity in general, the human genome as a kind of case study in probability and the binomial distribution, tax brackets as a case study in kind of piecewise defined functions, and then my favorite chapter to work on was about the Death Star. And in particular, sort of like the strangeness of choosing to build a spherical space station, what some of the consequences are of that geometrically. Anyway, so that was a fun book to write. After that, I did a book about calculus called Change is the Only Constant. And less about the calculations of calculus. I mean, calculus, right, etymologically is, you know, the word calculus comes from the pebble you'd slide around an abacus. So it's supposed to be like abacus math, but for, you know, infinitesimal changes. That wasn't really what I focused on in the book as much. I wanted to talk about stories. So it opens with a story about what would happen if you could freeze time, sort of isolate an individual moment. And then, of course, the story of the apple falling on Newton's head, which is obviously made up, but he told that story a lot himself, actually, later in his later years. You know, we have like 4 different sources of Newton talking about the apple falling, not on his head, just he watches the apple fall, which Newton, great mathematician, maybe not such a great storyteller, that he was like, yes, what everybody needs to know is one time I saw an apple fall. That's the big moment for me. The story of Brownian motion, which was fun to write and think about. And then one of my favorites is a story of Elvis, the dog who knew calculus, who became a media sensation about 20 years ago. That was my second book, and my third book was about mathematical games, came out earlier this year. So some of the games are mostly pencil and paper games. Some of them are sort of classics, like dots and boxes. Some of them a little more obscure. So one that I found that I really liked was a physics teacher had come up with rules for quantum tic-tac-toe, which is love. I had never took any quantum mechanics myself, but I felt like I had a better idea of kind of superposition and the collapse of the waveform based on this game. Definitely the most complicated tic-tac-toe game you will ever see. And then a few of the games are ones I made up myself. So I made up one called Dandelions, where you've got the 2 players are the dandelions and the wind, and they're fighting for control of a field, the little meadow that they're both the dandelions are trying to fill. Anyway, so those are my books. I'm very proud of them, but I'm not here today actually as in my capacity as a writer or as an author. I'm here as a teacher, which is to me sort of, although I've been a full-time writer these last 5 years now, that's still the role that's closest to my heart. And in that role as a teacher, with the class I'm teaching now and the classes I've taught in middle school and high school, a question that I always wrestle with, and a question that, I don't know, both interests me and excites me and kind of haunts me and frustrates me, is the question of when students look at algebra, what are they seeing? Like, what is going through their minds? What is the experience they're having, both cognitively, like how are they processing this, and then emotionally, like what does it feel like to be immersed in this strange language of ours, this language that we all speak fluently and that we enjoy speaking, and which for a lot of students is a barrier, can be the castle walls that are keeping them away from the ideas. What I've done in my books, up to this point, the first 3 books I've written, is basically done an end run around algebraic notation. I talk about mathematical ideas, but I pick very carefully so I don't have to teach you how to parse this equation or how to think about that inequality. And you can do that as a writer, because I get to pick what I write about. You can't do that as a teacher. You can't say, oh yeah, we're going to do math, but we're not going to do any math writing stuff. We're just going to pick fun ideas. Like, the students need to develop expertise in this stuff. They need to become fluent in this language. So what do they see when they look at it? I think it's helpful to think about a few particular pieces of notation and just contrast, what does this look like to us? What does this look like to a newcomer to the language? So I don't know how you feel when you look at this. I look at this and these are totally different objects to me, right? Like, you've got a quadratic, you've got an exponential. I have different associations with those. They suit different models. They come up in different scenarios. The growth rates are totally different. I think to the typical student, they look a little something like this. Like, granted, they're different, right? Like, I don't know if you look, there's like a little blue swirl up there, orange over there. So like, yeah, they're different, but they're not meaningfully different. They're just like, I don't know, they're just like 2 colors all mingled together, and who knows what they mean. Of course, what I'd like them to see is something more like this. This is sort of what it feels like to me. If I, going back to, right, x squared, right, I don't know, you think about the growth rates, right? Plug in x equals 100. 100 squared, that's a big number, that's 10,000. That's like, if we're talking, say, pounds, that's like the weight of a couple of pickup trucks. Or if we're talking kilograms, like bigger pickup trucks. But same order of magnitude. 2 to the 100th power, right? And we're just at 100. We're not talking way, way big numbers. 2 to the 100th power, that's about 10 to the 30. So we're not talking 2 pickup trucks or 4 pickup trucks. We're talking like 100,000 Earths, right? 100,000 times the weight of the Earth. That's 2 to the 100. These are totally different objects. So, but I know this is how they feel to students, right? They don't feel that different. Another one that I think looks very different to us than it might look to students, I'm sure many of you have taught how to solve equations like this, to the point where this is like reading English for me, right? It's just like I parse it immediately. I don't need to go letter by letter. I think that is not how it feels to students. I think reading it, they read something like this. Like, just this kind of anxiety monologue starts going through their minds. And what they're doing in particular, right, like 0, like, okay, I know what 0 is. This other stuff, I don't know. There's parentheses. In particular, I think what they're doing is they're looking at a very fine-grained level. They're trying to assemble all these little pieces, like looking at a disassembled Lego set on the ground. And like, oh my gosh, how does this fit together? What am I supposed to do? There's a little blue piece, there's a little green piece, there's an X, there's a minus, there's another minus, there's another X, there's these parentheses, and it's all these little scattered pieces. And what we do as experienced readers of math, and it's a little different than what experienced readers of English do. English, we really do read left to right. I think what we do as readers of this is we immediately sense the overall structure. And so to me, it looks something like that, right? What I'm looking at is 2 things multiplied together. And like, I don't really care what those 2 things are. I could dig into the details and like, yes, they're each linear terms. And so each one will give a unique value of x if you set it equal to 0. But basically what I'm looking at is 2 things multiplied give 0. And I just know from my experience of math, one of them's got to be 0, right? Like, it's not going to be 3 times 4 equals 0. That just doesn't happen. It's got to be, of the 2 numbers, one has to be 0. So I'm bringing in a bit of my background knowledge to how to read it, but mostly I just know how to parse the structure. One more, and Right? It's exactly the reaction I get. I've done this with smaller groups of occasion. At a few two-year colleges before I myself started teaching two-year college. I did a few little training sessions, little chances for faculty to discuss, classes they were teaching. And that's exactly the reaction I get every time I show this one. Because I think you look at this and you just start, you just have to groan. Because you're picturing the experience it'll be of the tooth-pulling dental surgery experience of trying to get students to sit down and be patient with this equation and not just run for the hills. I think it's a fair expectation. You put this up on the screen and just the classroom empties out, just books are thrown down, people are running for the corridors. This, I think, when students look at this, I think what they see is something like that. I think an equation like this is just the face of death. And I get what they mean. Again, I think what's going on is they're reading in a very detail-oriented way. They're looking at all the little pieces and trying to think, okay, how does that piece go, that piece, that piece? They're not seeing it as an overall structure. Because I think when those of us who are in this room and speak mathematics fluently, when we look at this, we can immediately tell kind of what the outermost layer is, right? And so I read this again as that big fraction within a fraction. Now, I don't like fractions within fractions. I'm going to be multiplying numerator and denominator by something to clear out the inner denominator. But I don't need to worry about that right now. It's just some number, some big, ugly number. With students, I'll actually sometimes draw a little monster around it. So more bad drawings, but with a little mouth and angry antennas and angry eyes. Be okay, the monster, yes, it's a scary monster, but don't worry about the monster. Monster minus 3 is 8. You know what that monster is. Right? The monster has to be 11. You can think of it as adding the same thing to both sides, or just fill in the blank. The monster has to be 11. But again, this is how I feel as a fluent speaker of math, as someone who's enjoyed this language and felt comfortable with this language for a long time. That's not where students are necessarily coming from. So I've got some thoughts on how to unpack this for students. But it's hard. Actually, let me pause before I go to that screen. It's hard stuff. And again, I avoid this stuff in my books because it's not something you can do from a distance. I can't be sitting in my office in St. Paul writing a book and teach this kind of experience to students thousands of miles away. It just doesn't work like that. If you want to learn to speak a language, you got to talk to somebody who speaks the language. There's really no substitute, I think, for a teacher there in the room with you, being patient, developing a relationship, having a conversation. That's how you learn to speak a language. And so I want to take a minute. I've been talking for about 10, 15 minutes. I want to pause here and ask a question for you to talk at your tables for a minute, and then we'll share insights if you want to share them. I think I have some microphones that can get passed around. But just thinking about a particular, sort of as specific as you can make it, and think about classes you're teaching now or classes you've taught recently. What's a particular notation or bit of algebraic symbolism that you feel like your students struggle to see or struggle to read? When they encounter it, it has that kind of paralyzing effect. Inverse notation, cool. Let's do a quick conversation at the tables. So just, you can go around at your table, talk about it, and then I'll bring your attention back up front in 2-3 minutes.
These are your two runners.
Excellent, thank you so much. Yeah, I'll call on you in a minute for that. How's it going? Yeah.
9 divided by 9 to get F.
Yeah, right. Oh yeah, just cancel it out. Yeah, sine x over x. It's just sin.
Yeah.
Yeah, there you go. Yeah. Yeah, that's one I think. The parentheses. I wish we used square brackets or something, right? Because the parentheses. I've had so many conversations where it's so f times x. It's no, it's not times.
Yeah, I actually prefer it what they'll use in sequences or series where it's subscript.
Oh sure, yeah.
Right?
Yeah.
Because it's I feel like that notation is just, at least it's not as.
Right, they don't already have associations with it.
Yeah, exactly.
Yeah, that's true.
Oh yeah.
It's such a mess.
Sine to the -1.
Right, but sine squared is sine to the is sine of x squared. Yeah.
Trust me.
Yeah. 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 No.
Just for that matter.
Log in this class and only this class is base 10. Everywhere else is base E.
Right. Yeah, that is frustrating. I know. I was talking to my dad about this. I was like, so what do you think? Is should it be base 10 or base E? He was like, that's crazy, base 2. I was like, what? Because he does theoretical computer science stuff, and so it's okay, all right, I guess log could be anything. How's it going?
On what you said.
Can I just listen in for a second? What's coming to mind for
Any fraction.
fractions? Yeah. Fractions are tough. Yeah, I mean.
I think the function notation too.
Yeah.
Because there's a lot of like, it's not multiplication. Sorry.
Yeah.
And they want to multiply f times x.
Yep. Yeah. No, that's right. Yeah. I have that conversation so much. They're like, no, we're not multiplying, right? Yeah. Yeah, that's tough.
And then in probability and stats courses, it's the same thing.
Right. P of. Yeah. Or E of. Yeah. Yeah. Yeah.
And she mentioned my nightmare this week, which was chi-square. We just talked about it right before I came here.
Well,
and
that's
I've
just
had emails.
that's just hard to draw. I mean, just drawing the chi, trying to get that curve just right. I mean, there's some symbols. Occasionally, if psi comes up, that's like the little squiggly. Is that the one?
Oh yeah.
Impossible to draw.
I just showed that one off.
Yeah. If you got the handwriting for it, yeah, that's a good way to go. Hey, just listen in. Sorry, how's it going? What's coming to mind?
Logs.
Logs, yeah.
Oh my God,
yeah.
I hate them.
Logs are a mess. Yeah.
Radicals. Square roots.
Yeah,
Square
yeah.
roots.
Yeah.
The square root of 4 is the square root of 2.
Oh, sure. Okay, cool.
And in developmental math, they have a hard time, like difference between 3x versus x plus 3.
Yeah.
They-
Sure. Yeah.
It's very hard for them to understand what's the coefficient versus the constant added to them.
Yeah, sure.
Calculus students still forget, like your constant multiples versus your plus 3 becomes a plus 0.
Right. We're trying to apply differentiation rules or whatever. Yeah.
They've moved on.
Right. No. Yeah. They've taken a lot of math at that point. Right. Yeah. Yeah.
Multiplying multiple terms, and they think that coefficient at the beginning belongs to one of them only. And when you take it out, oh, why did it affect the other one?
Yeah. Huh. Yeah.
But logs is always been the big hurdle for
Yeah. Is it pre-calculus is where this is showing up, or in pre-calculus? Yeah. Yeah. No, logs are tough. Yeah. I mean, it's a weird, and sometimes it's a weird concept, right? Like, I don't know, the inverse of the exponent. It's like, it's a tough one. Yeah. Cool. All right. Well, yeah. Thanks for sharing. How's it going? All right. Well, I guess it sounds like my mic's coming back on, so I guess time to talk. All right. Thank you all so much for having those conversations. Let's take another 30 seconds, minute to finish them up. All right, and as you're wrapping up those conversations, I'd love to hear some of the specific discussions that happen at tables. So it's like the same problem I always have when I have students do discussion, but times 700. Yeah, that's fine. Yeah, people just want to talk the rest of the time. That's, I get it. All right, so I'll do my classic middle school teacher countdown. We'll do if I could have your attention back up here, please, in 5, 4, 3, 2, 1, and 0. Thank you. All right. Yeah, I miss teaching 6th grade, actually. That was a fun gig. All right, the couple tables I managed to stop by were having really interesting conversations. I would love to hear a little bit of stuff shared between tables. We have some microphones, in both of the wings. Yeah, there we go. Thank you so much. Does anyone want to share what their table was talking about? Sort of be the representative of your table, just share what came up for particular challenges. Okay, I heard equal sign over there. You want, let's share, someone's got a mic over there, I think. Yeah, sorry, I'm a little blinded by the lights, but yeah, go ahead.
So the notation we use for inverse/-1 exponent is married with parentheses and all the meanings that parentheses have, or if you're writing natural log, don't have because they magically disappear or sometimes appear and such.
Yeah. Yeah, I think parentheses is an interesting one. This is, I think of parentheses almost as like commas in mathematics, right? They sort of organize the thought, they divide thoughts from one another. Sometimes they're almost stylistic, right? Like so there are different writers who will use a comma here, won't use a comma there, and that taste varies. And sometimes they're totally necessary. And that's hard, right, to have something in parentheses or like this, where like sometimes you need those parentheses because if you don't include them, you mean they're saying something else. And sometimes they're more like an organizational tool that's helping show what goes together. That stuff, yeah, and inverse notation is, yeah, that's, when I have this conversation with people, that's one that comes up a lot. I think, to me, I trace that back to exponent notation being really weird and hard. This is something, doing the research actually for the book I'm working on now, it's called How to Speak Math. I was reading the sort of like this classic history of mathematical notation by, some fancy Italian guy name from like, about 100 years ago he wrote it. And the interesting thing to watch is as you read about, 14th, 15th, 16th, 17th centuries, just the nightmare for exponents. Nobody had any good way to write exponents. Usually, like most of what people do in algebra is they just call, like have little abbreviations for the thing, like CO for cosa, the thing, and then let's see, what would square be? Maybe I don't know what it is in Italian, but it'd be like QU for the square, and then CU for the cube. And you probably didn't talk about a fourth power because that has no geometric interpretation. But you had totally different notations for squares and cubes. The idea that it's x to the 2 and x to the 3, which unifies it very nicely. It's beautiful notation. Even that, like, really wasn't the way mathematicians wrote it or thought about it for a long time, much less bringing in reciprocals like x to the -3 or x to the -4, as though that's the same idea. I mean, in some sense, that's crazy, right? Like, you can't, x to the -2 is nonsense. But it's kind of lovely nonsense that brings the system into a nice harmony. That's hard to explain to someone learning the language. Anyway, sorry, that was a long ramble, but yeah, I think that I'm sure many people in the room feel the same way about those notations. Do we have another table that wanted to share? I won't ramble as long this time.
Our table ended up talking about function notation and how often students are used to two things next to each other. You multiply.
Yeah, I feel like I could have that conversation every day of my life and still feel like I haven't had it enough with students. Yeah, right, that those parentheses aren't multiplication. Yeah, that's a tough one. Yeah, back there.
Logarithm notation.
Yeah. I was talking to another table up here. I was talking about logs. Yeah. Logs are tough because it's a slightly unnatural notation for what is already a pretty subtle concept. So you've got a barrier of language before you can even get to what's a pretty tricky idea. I enjoy, when I talk about logs, I enjoy talking about, again, kind of the history of it, where like the point of a log is to turn multiplication into addition. That's what it's for. Because if you don't have a calculator, multiplication is real slow. And if you don't have a calculator, what you want to do is you want to take your book of logs, look up your two numbers that you're multiplying, look up their logs, add the logs, do a reverse lookup, and then you're done. That's where logs come from. That said, having had that conversation with the students, they're not that impressed with that. Somehow my waxing poetic about John Napier doesn't inspire them. So, logs are a tough one. Were there other tables? Yeah, over there.
Did you want -2 squared? Yes.
Yeah, that's one of the ones I remember in middle school when I first encountered that. I was convinced my teacher was wrong, right? It was like -3 squared, right? A -3, and then the 2 is -9. I was like, no, it's not. No, it's not, Ms. Perrone. You gotta check your numbers again on this. And it took me a long time, and I think it's one of those things where when you're just doing it with numbers, it seems weird. It doesn't make sense. Why would -3 squared? -3 is a number. It seems like its own unit. I shouldn't need parentheses around that. But then when you get into algebra, of course, -x squared should be the opposite of x squared. That one feels much more natural to me. So it's tough. And this, I think, often happens in math. The language was built for algebraic purposes and for fairly sophisticated ones, to make calculus work or to make polynomials easy to discuss and describe. But then we take that language and we apply it to numbers, and it's like not actually a very natural. It's a little clunky for talking about numbers sometimes, and that can be very hard for students. Although it's not so you can just throw them in the deep end and be like, all right, let's talk about arbitrary degree polynomials. Now you'll understand. You got to find an entryway, a way to bring them in at the ground floor. Was there another table that wanted to share? Yeah, let's do one or two more.
So we said logarithms also, but the higher order radicals, so like 4th root, 5th root, that sort of thing.
Yeah, I think even square roots can be tough. Yeah, I heard, right, there was one table noting that students will often write root 4, and then they'll write root 2. I was like, oh yeah, incredible. You can just write, imagine if you started with root 256, you can just shrink it and shrink it and shrink it. Root 256 is root 16, is root 4, is root 2. Bam, wow, that's, root 256 is also irrational by that argument, which is impressive. Yeah, that's a tough one. Yeah, that's something I think about a lot. I'll talk about more, I've got some slides on it, but the difference between math where you're trying to do, you're trying to take an action, versus math where you're happy to just kind of let it sit. Like root 256, maybe I can simplify it, but maybe not. It's a number, it's root 256. That's a transition that I think is hard for students. Did we have one more table that wanted to share? Yeah, let's do this, our last one.
How about the inconsistency with multiplication sign? We teach students in elementary school that x means to multiply, and then later on, x becomes a variable, and we change multiplication from an x to a dot to parentheses. It gets confusing, so I wonder why we can't just begin with a dot or some consistency from day one. Thank you. Thank you for allowing me to share.
I appreciate it. Well, there you go. All right, you've got, I'll tell you, circulate a petition. It seems like you got support in the room. Yeah, that's one, the multiplication thing is really fascinating. I lived in the UK for 3 years and taught secondary school there. And there was this bizarre phenomenon where, I guess in older textbooks, like my older colleagues, had the experience of having the dot at the bottom, where we would put the decimal point, meant multiplication for them. And the dot in the middle meant a decimal point. But of course, they then ran into American texts, right? Like, the UK is a smaller country than the US, so you wind up with American mathematical texts floating around that do it the opposite way. So this just freaked everybody out, and they basically had to abandon the dot. Like, they try not to use the dot when possible. So what is multiplication? You have to use the x, that they were forced into that symbol. So what do you do with the x? You have to draw your x in this funny kind of curvy way. My students got so mad my first few months at my x's because I did these little straight line x's. And they're like, what is that? That's not a real x. That's not a proper x. And to learn to draw a proper British x, which kind of has curvature to it. I don't know, our language is a mess. I mean, in some ways, mathematics is just as bad as English with all our terrible spellings. And we've got weird etymologies in mathematics too. Yeah, thank you so much for sharing. It's really fun for me to hear, the thoughts, and interesting to see, for one thing, a lot of different ideas come across the tables, but it's a similar handful of things. It's functions, it's exponents, it's radicals, it's various iterations of functions like trig functions and inverse trig functions, which is the combination of functions and exponent notation. It's a lot of the same things. So what I'm going to do, I've got about 20 minutes left. I'm just going to solve all these problems. Once and for all, design a new and universal mathematical language. No, what I'm talking about one symbol that I think lies at the heart of a lot of this. Not all of it. I'm afraid I can't solve all of our problems as teachers, but one symbol that I think is really crucial, which is one that someone mentioned earlier from over here, I think actually, the equal sign. This is a cartoon, by the way, of when I first moved to St. Paul. I haven't seen them in a while, but I would run over the bridge between the Twin Cities. So the Mississippi River runs right between St. Paul and Minneapolis. I'd be going for a run, go across the bridge, and right on the bridge, the Lake Marshall Bridge, there would be these protesters, half a dozen people maybe, probably in their 60s. It's Minnesota, so they're bundled up, hats and coats and scarves, and holding just the vaguest protest signs. I had no idea what they were protesting. I really I think I agreed with them. They seemed like mostly they were against war, I think. I agree, low number of wars, definitely better than a high number of wars. But the one sign they had that was my favorite of theirs was just an equal sign. There was something very cool about that to me, that here I am out in the world. These people I think are probably not, maybe they're passionate about math education, I don't really know. But here they are with this symbol. I know a little bit of the history of this symbol, right? This is usually attributed to Robert Record, a wealth mathematician from mid-1500s. Probably predates him, or it's probably used in the Arabic-speaking world for a century before that. A symbol that almost vanished, actually, from mathematical history because Descartes had an alternative, this little kind of backwards lowercase alpha fish-looking thing. Wretched symbol. I mean, we're so lucky we are not living in the alternate timeline where we denote equality with an asymmetric symbol. It would be horrible. It was Leibniz who looked at that, mostly used Descartes' notation for stuff, but was like, no, we're not doing that. We're using this nice symmetric one. So think about all that history and being like, it's just funny to see protesters with an equal sign. that somehow this like mathematical symbol comes out of the Arabic-speaking world into Wales, into the rest of mathematics textbooks, that's their symbol of protest, was interesting to me. And it's interesting partly because it's one that I think students really misunderstand. And maybe that's not fair. Maybe it's not fair to say they misunderstand it. I think they have one way of understanding it that is not the way you need to get through an algebra class and to get deep into calculus. That they're bringing one kind of understanding that doesn't carry them through into the kind of mathematics we'd like them to reach and have access to. They're speaking it's almost, you could think of it as like a colloquial, vernacular, street language kind of equal sign that they're using. And what we need them to learn is a more formal, scholarly, a different kind of way of using the equal sign. And this is hard. So like as a writer of popular math books, the story that I think of as very famous, although maybe not that famous, is when Stephen Hawking was working on A Brief History of Time, right? Huge best-selling book about well, time and a brief history thereof. He was told by his editor, don't use equations. Every equation you use will cut your readership in half. Which is pretty grim. It's like a very difficult technical book, as popular science books go. But he only used one equation in the whole thing. The equation is E equals mc squared. That's his only one, and sold 1 million copies. So I've got a slide with my illustration. I don't have the actual cover of the book. Now, to me, you include one equation, you sell 1 million copies. According to the editor's logic, what they should have done is cut that equation, come out with a second book, one equation shorter, just don't say anything about whether E does equal mc squared or doesn't, sell 2 million copies, right? If every equation loses half your readership, then you're leaving a lot of money on the table. So a part of me wants to rebel against that, right? Like every equation, an equation is just a statement that two things are equal. What kind of statement that two things are equal could lose half your readers, right? Are you saying if you said puppies equals Nazis, that might lose half your readers. That would be a very offensive equation. But E equals mc squared, why would one equation lose half your readership? And I think, of course, having written, well, not books that sold 1 million copies yet, but books like this myself, I get why you avoid them, which is that people don't read them as a statement that two things are equal. People are reading equal signs a little differently. And you know this from the classroom, right? Students don't read an equal sign as just a verb meaning is equal to. They're reading it some other way. And for me, trying to understand how they read it, this is a study I came across that asked students questions like this. And the answer was telling, and I think captures how they're seeing the equal sign. We look at this, we all know what goes in the blank, right? The left side is equal to 9, the right side has to equal 9, so the blank is 6. But my guess is many of you, I bet, will be able to guess what the most common incorrect answer was. 9, right? Lots and lots of students write 9. And so what's going on there? I think what's going on is not so much that one interpretation, I don't think this is quite it, is that they're just reading left to right the way you would read English, and not realizing that mathematics isn't just a left to right language, that there's something a little more holistic and spatial about the way we read math. That could be part of it, but I don't think that's the main effect here. I think the main effect is that when you're coming out of arithmetic education, math is about doing things, right? You first learn to count, meet all the numbers, see who they are, see where they all live on the number line, and then you start doing things with numbers, start combining them, multiplying them, adding them, subtracting, dividing, eventually exponentiating. And so math is doing. And the equal sign is, I think of it as like the ta-da. It's there, or the drum roll, right? What an equal sign is it's 7 plus 2, drum roll, it's 9. Ta-da. And so they're not seeing it as a verb meaning is equal to. I think they're reading it as a drum roll, as a ta-da, as some kind of exclamation. At one point I was thinking, someone had an interesting hypothesis that this is because of calculator notation, right? 7 plus 2 equals is like enter, do the calculation. But in fact, this error is maybe the wrong word again, this interpretation of the equal sign is you can see it in the literature going back well before there were pocket calculators readily available. So I don't think it's that this is from calculators. I don't think it's just the left to right thing. I think this is actually a very natural way to understand the equal sign if your experience of math is arithmetic. Because there's a big difference between the mathematics of numbers and this algebraic world that we want students to get to know, right? Arithmetic, we see expressions like this. Algebra, we see expressions like this. I don't see these as terribly different, right? My experience as a fluent speaker of mathematics is like, okay, it's 7 times a square. The other one is 7 times a square. The square happens to be 3. Okay, so that we're talking about the prime factorization of 63, but they're similar sorts of objects. And as you know, to students, they are not, right? I think most students experience 7 times 3 squared as a set of instructions, right? This is a set of commands. It's like, this is what you're supposed to do. Now do 7 times 3 squared. And they're tricky instructions because you have to learn PEMDAS. You have to learn that this operation comes before that operation, even though they're not written in that order, left to right. But it's instructions, right? And that's the way we teach order of operations, right? These are operations. These are things you're doing. Here's the order to do them in. But that's not algebraic thinking. And that's not algebraic writing. And that's not the way we speak algebra. Algebra is about objects. So in linguistic terms, right, this is an imperative. That's how students hear this, I think. Like, jump, that's an imperative, right? Like, go over there. Run screaming to the hills, right? Like, those are imperatives, right? A command telling you what to do. I think that's how they hear 7 times 3 squared, like, do it. And algebra is not about imperatives. Algebra is about declarative statements, right? This is actually not, right? 7x squared is not a statement because it has no verb. It's just a noun. But equations are all declarative statements. It's saying this thing equals that thing. It's a declaration, right? It's like saying Toronto is the capital of Ontario. I'm not asking you to do anything with that, right? Like, you don't have to go, I don't know, like, tell everyone, or I don't know, go to the top of the CN Tower. I'm not giving you any commands. You don't have to leave. You don't have to get up. I'm just saying Toronto is the capital of Ontario. It's just a fact. And so in simplest terms, I think arithmetic, as it's learned, is about actions. It's about doing. And algebra is about things. In fact, one of my favorite terms for algebra, right, medieval term, people would call it cosism, right? And so algebraists were cosists, which literally means like thing, right? Because instead of x, they didn't use the letter, they would say thing. So like the thing squared plus the thing is equal to 12. What's the thing? And so this is what algebra is. Algebra is about declarative statements about things. It's not to say we don't want our students to do anything. Some days we would like them to do more than they're doing. But it's that the language itself is not a set of commands. The language is a set of statements. That is a very weird and hard transition for students to make, I think. So what I want to do I've got about 10 minutes left. I want to use that time to think about how to help students see this and experience this transition, to think of equations as statements, as giving information. Let's do it. The conversations at the tables are fun, I think. So let's take just maybe 3 or 4 minutes this time. Yeah, like 3 minutes. And share what is your favorite equation, or it doesn't have to be your single favorite equation, a favorite equation of yours. I think I find this a nice starting point for starting to think of equations, not as instructions, but as statements. Good.
That's not my favorite.
Favorite equation?
That's not my favorite, but that's the one that always
Oh,
comes up.
that's a classic one,
right?
yeah.
I'm a trigger. I guess I like sine squared equals cosine squared equals 1.
Oh, that's beautiful.
That's my favorite one.
Pythagorean identity. Yeah, I like that.
You don't have one?
No.
You don't have one? No.
2 plus 2 equals 4? 2 plus 2 equals 4?
Yeah.
It's a classic, timeless. Oh, right, well, yeah. No. 2 plus 2 is greater than 3. No, there we go. Hey, how's it going? Hey, favorite equations?
I like from like a physics perspective, I like Euler's equation.
Sure.
And like the Maxwell equations.
Oh yeah.
But like I was trying to think like equations in my classes.
Students hate equations. They don't know how to use them.
No, yeah.
Right? Yeah.
You like the quadratic equations?
I do like the quadratic.
Right?
Yeah, we don't. It used to be really good because
the calculator didn't immediately give the answers to a quadratic equation.
Sure. Yeah.
And now when I show my students the negative b plus or minus the square root, they don't know that anymore.
Sure.
It's just go into equation mode.
Right. Sure. Oh, right, of course, it'll solve it with radicals too, right? I mean, it gives you the precise solution.
Yeah.
It's not just a numerical solution, yeah, right.
Yeah. I like maybe they're not equations, but I like the special product equations. So like, they give you equations for factoring, quadratics. I like using them in reverse to speed up like finding the product.
Oh, sure. You mean like for like a plus b squared or something, or a plus b times a minus b. Yeah.
So if I'm asked to expand like x squared plus 4 and x squared times x squared minus 4, I like knowing that that's like difference of squares, and I can just.
Yeah.
And I like teaching that.
Yeah. No, I like that stuff. Yeah. 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 Cool. All right, so that was just a brief moment to share your favorite equations. So we'll go back to our 6th grade techniques. If I could draw your attention back up to the front of the room in 5, 4, 3, 2, 1. Didn't work. Well, you guys remind me of my favorite 6th grade classes. It was fun memories. Yeah, that was a fun job. Yeah, it was the UK, right? It was a boys' school, so 25, 26, 11-year-old boys just absolutely bouncing off the walls. Good times. Anyway, thanks for discussing the equations. Did anyone want to share? We could share a couple of the favorite equations. I would love to hear. Yeah. Beautiful. Pythagorean theorem, right? Timeless. Does he in the back? Yeah.
E to the pi I plus 1 equals 0.
Right. Another. Oh, there you go. You could run a campaign with that as your platform in here. That's a popular equation. Over there.
Yeah.
Sure.
That's what I was going to say.
Yeah. Right. Sure. Yeah. Quadratic formula. Yeah. Do we have another?
No, that's what she's going to say.
Oh, okay, cool, yeah.
We're singing it.
Do we have 1 or 2 more? Yeah, we just shout it out in front.
The normal distribution formula is mentioned here.
Normal distribution, so like the PDF for the normal distribution. Okay, cool, yeah, all right, we got everything's in there, right? We got radicals, we got e's, we got, all of it. Yeah.
Second degree polynomial equation in 2 variables.
In 2 variables, okay, nice, get some y squared in there. Yeah, always fun, get more variables involved, yeah.
1 plus 2 plus 3 plus 4 and so on is negative a 12th.
I'll tell you, it's a statement that has an equal sign in the middle of it. Does that equal sign mean exactly the same thing? I think the equal sign actually does. I think the question is whether plus and ... mean what we usually think of them as meaning. But certainly an exciting equation. Over there.
Red plus blue equals purple.
Oh, red plus blue equals purple, yeah. I like that, right. I wonder, it's interesting because I suspect red plus blue over 2 also equals purple. Yeah, the mathematics of color is an interesting one. I have to think more about that. Let's do 2 more, let's say, yeah.
All right, well, the sum of the natural numbers from 1 to n is actually n times n plus 1 over 2.
Yeah, sure,
That makes a little more sense.
Yeah, formula for the triangular numbers. Yeah, that's a lovely one. The classic story about Gauss, right? Like, 7-year-old Gauss told, go add these 100 numbers because I need to take a nap, presumably. His teacher was tired. And then, does it in a moment because essentially that formula works by you double the sequence and then pair up the largest with the smallest and the second largest with the second smallest, and you get this lovely sum. Way in the back. Let's do this. This is our last one.
Sine squared plus cosine squared equals 1.
Yeah, another, okay, maybe a rival for Euler's identity as a popular equation. Yeah, those are all lovely equations. I think one one very fair reaction to this question is that's not how I think about like I don't have a favorite equation. That's not how I think about equations. They ask me if I have a favorite tax law. Like I don't know. It's just they're statements of truth. They're not like I don't have like fond feelings about them. They're not lines of poetry to me. But I think it's worth trying to cultivate a bit of that sentimental attitude towards equations, to start feeling them like there is something poetic in equations, right? And in stuff like sine squared plus cos squared equals 1, there is something I think rather lovely going on there, just as a statement of truth about this strange mathematical world that we imagine. I think there is a kind of poetry there. So we tend to think of mathematics as a technical discipline, right? You are mastering a set of skills. And indeed, you are. That is a big part of what mathematics is, right? It's same as when you're learning to play the guitar. You got to learn to do your fretwork well. You got to learn your fingering patterns well. Like that's the skill is there. That's part of the discipline. That's a big part of what you're doing. And so it is in mathematics, right? To be a skillful and thriving mathematician, there are a lot of skills you got to learn. You got to learn how to solve these kinds of equations and those kinds of equations and how to read this kind of graph. So there's a lot of skill there, a lot of technique. But I think math is broad, math is expansive. And so we can also imagine mathematics, the way I've been talking about it today, as a language, and then beyond that as a kind of culture and even as a kind of literature. So real quick, I'm running short on time, but a story when it comes to, well, reading and understanding literature. High school, I had to read a little bit of Hemingway. Anybody else have to read Hemingway? Didn't get it. I just didn't get it. Like, it's not that I couldn't read the sentences. The sentences are all short monosyllables. I certainly could read the sentences. I did not get what he was talking about or why it mattered, like what his attitude was. I mean, other writers who I think of now as like more difficult in some ways. We read D.H. Lawrence that year. We read some Dickens. Read Things Fall Apart by Chinua Achebe. Like, we read other books that are subtle and tricky, and those made more sense to me somehow. Hemingway I just didn't get. It was when I had to write an essay about Hemingway. Spent the whole night retyping the short story that we were reading and writing the essay on. I just like retyped the thing, trying to go word by word, like what is he talking about? Why is he saying this stuff? And it was just a bad essay. I couldn't quite figure out what he was talking about. I mentioned this a few years later in college to a friend of mine named Mike, a very wise guy, Mike, and he said, okay, what I've heard with Hemingway, can't read Hemingway until you've done 3 things. You need to have gotten blackout drunk. You need to have been in a fight. And you need to have fallen in love. And I was like, how to explain why at age 15 I did not make much sense of Hemingway. And I don't know much about this, these specifics. I don't know if I can vouch for this. I would say I've not quite made it to blackout drunk, and thankfully have not been in a fist fight myself. Had at that point, when Mike told me this, I'd already met my wife. So I was there towards maybe understanding a bit of Hemingway. But whatever the specifics are, I think the general idea holds, which is that to read literature, you need to have some experience of the world, right? Great books are talking about something, right? They have themes that touch on our lives, and so you can't really appreciate those in a vacuum. You need some lived experience. You need some sense of what they're talking about, even if it's not you've been bullfighting or you've had exactly that experience. You need something in your own emotional life that it can touch on. So my question is, and this is something I think about, to read a bit of mathematics, what are the experiences that our students need? What do they need to have done or seen or felt or thought? And when it comes to equations, I don't think it has to be a fancy experience. The experience I try to give is just seeing that there are different statements. Not limiting myself to the handful of hand-picked, super efficient, effective problem-solving statements that we put in the textbooks, but just like the whole realm of things you can say with an equation. So some equations are what you would call sweeping generality. We call these identities. And with an identity, I think you can think of it either as the cartoon says, either as kind of universal wisdom. Yes, 2x plus 3x equals 5x. That is always true for any x. What broad and sweeping wisdom. Or you can view that as just a self-evident triviality. Like, you need to know what you know. It's like, okay, well, that's helpful. Thanks, man. There's something about tautologies that are like that, and so a task I like to give students when we're sort of getting into this part of algebra is just give me 5 statements about x that are always true no matter what x is. And the students will come up with interesting things in the class. They'll surprise me usually. The statement, right, doesn't have to be an equation, just any kind of statement. It can be an inequality. You can use English words if you want. But let's just talk about numbers. What's a thing that's always true about numbers? Okay, not all equations are always true, of course. Some equations are just brazen lies. And that's different than a regular lie, right? A regular lie would be like if I said, my height is 6 feet 3 inches. That's just a lie, right? Like someone could say that and it would be true. It's not true of me. Whereas if I say my height is 3 inches taller than it is, that's a brazen lie. That's like you can't say x equals x plus 3. It's just never true. And so again, I'll ask students, right, give me 5 statements about x that are never true, no matter what x is. This is tricky. Students will come up with things where like, this doesn't seem like it could be possible, and then actually maybe it is sometimes, and that itself starts a good conversation. Most of the equations we run into, I think, are essentially gossip, is the way I like to describe them. So you say something like, the text is probably too small to see in the back, but something like 3x plus 2 equals 22 minus x. What we're saying is, there's this number out there, did you hear? There's this number. If you triple it and you add 2, it's the same as that number taken away from 22. It's not interesting gossip. It's not the most fascinating gossip. But it's structurally it's the same as gossip. It's like when you say, right, if I say like, I think somebody ate the last cookie, that's a statement. It invites a question, which is, who's the somebody? But I'm actually not asking you to do that. I'm just giving a statement. Somebody ate the last cookie. Somebody forgot to close the fridge. Somebody seems to have stolen all the juice. I have a 3-year-old in the house, so usually clear who that is. So again, another task I like to do is just write 5 statements that are only true when x is 4. Or as you get into more challenge, give me a statement that's true when x is 4 or when x is 6, but only those 2 values. And they might have to invent quadratics, or they might just write x equals 4 or 6. And you go, okay, that's fine. Because they're starting to speak the language. That is the simplest answer, x equals 4 or 6. Or is not the most algebraic notation, but not bad. And another thing I like to do is, and this isn't something I've actually tried with my current crop of students, but is play with the notation. So this is something I do a lot. I do cartoons for Twitter and Facebook, and well, Twitter, RIP Twitter. But I do cartoons, and so things like this, they're just playing with mathematical notation. I think I was probably listening to some Beatles solo stuff while I was doing this, and noting that the top statement, so loving the sum of 4 musicians, versus the sum of individually loving 4 musicians, these are not equivalent statements. Yeah, I'll tell you, yeah, Ringo's solo career doesn't always, I mean, he's got some good hits, but doesn't always do it for me. And so, right, translate that, love is not distributive over musical acts. And once you've got the line, this is kind of, I mean, this is a silly version of fluency in mathematics, but this is sort of one thing it can look like, is being able to play with the language and use it to say things that, I don't know, maybe aren't the obvious things to say, or don't even feel very mathematical. But there's something mathematical about this. So back to those protesters on the bridge. I was thinking about this. I was working on the book I'm writing now, which is How to Speak Math. And those protesters, who I think I was ungenerous towards when I ran by them, because I was thinking like, okay, well, like I don't even know what they're protesting. What are they up to? But think about, there's something, yeah. Looking back, I found something kind of beautiful in the protests they were making and the form it took. Because what are they doing? They're standing atop this bridge, right? This great structure of connection between 2 twin cities, right? 2 equal things, and they're holding this equal sign. And I think in a way, their understanding of the equal sign is perfectly sophisticated and true. What they're saying is a statement. They're saying all people are equal. And in a way, I was mishearing it. I was like, what are they telling me to do? Who are they telling me to vote for? Right? What's the command they're giving me? I was thinking very arithmetically. But in a way, their protest was much more in the spirit of algebra. They're saying, here's a statement. People are equal. That's what equality is. That's what equality means to us. And so I think I tip my cap to the protesters on the bridge, and I hope that they achieve what they are looking for. That is what I have for you today. Thank you so much for listening. And I think, do we have time for questions, or do you want to do time for questions, or did I run too long? Sorry about that.
Okay.
Sorry.
Stay here.
Okay. All right.
Thank you, Ben, for a wonderful talk. We appreciate you coming to join with us, and we do have a certificate to present, and we'll take a picture.
Oh, great.
Okay?
Yeah.
We're on that.
Yeah. Cool.
Stand on our marks.
Cool.
anything up
so much.
here, I'll let
Yeah.
people know to come up and ask.
Sure, yeah. Okay, yeah, that's great.
If you have any questions for Ben, we don't have time right now, but he will be hanging out at the front of the room. So you can come catch up with him there. All right. I would like to invite Kate Kozak to come up to the podium. There we go.
So I'm here to talk about the AMATYC Foundation. I want to thank all of you who got your dots. I hope everybody got their dots. If you didn't get a dot, there's still time to give money to the foundation, though you can't get dots anymore, but you can at least give money to the foundation. We did have 4 prizes this year to give out, and I want to award those prizes. We had the regional competitions were back, so we had a regional competition for the region that gave the most money, and then we also had a regional competition for the region that had the highest percent of people donating to the foundation. This year, the foundation had a goal of raising $30,000, and I will glad to admit that we're only about $2,500 away from that. And there's still time to give money to the foundation. So let's see if we can't reach that $30,000. Don't forget, we are a 501c3, so those of you who are part of the United States, you can actually write that off your taxes. So please give that money to that. So we do have, like I said, we have winners of the largest percent. Well, actually, let's do the highest donation. That region actually is the Southwest region. So I have to admit that I'm kind of excited about that since I live in the Southwest region. But so the Southwest region, the prize we're giving out to the region that gave the highest was we gave it out to one person we randomly drew from that region. They will be getting an AMATYC 2-year membership. And so that is going to Alberto Izazi from El Paso Community College. Then we also had the region that gave the highest percent of their members. Since July 1st, we were looking at how many members each region had, and the region that gave the highest percent is the Southeast region. And that's going to give you a AMATYC 1-year membership, and that is going to Ryan, I'm going to do this wrong, Pescasolido from Wake Tech Community College. Then all of the people who donated to the foundation since the start of the year were put into a drawing for just a discount registration to the AMATYC conference in Omaha. And I know you're all going to go to Omaha, and we're all so excited about Omaha. And I can't wait to go there myself. And so the person who's winning that is Dory Haggerty from Valencia College. And this year we had one more prize to give out, and that was the thanks to Karen Gaines for making this absolutely beautiful quilt. I hope all of you went to see it. Some of you went and saw it and said, oh, I want to get that t-shirt, and thought we were selling t-shirts, but we weren't. It was actually, she made these from math t-shirts, and that person who was randomly drawn and chosen for that is Leah Lance from Glendale Community College. So I want to thank you all for giving to the foundation. And again, if you haven't given to the foundation, or if you'd like to give more to the foundation, please give money before the end of the year and help us reach our $30,000 goal. Thanks.
Hang on a second. So Sean Saunders just came up. Apparently, the local events committee has one more toque. The local events committee has one more toque available. And they're willing to award that to the person who pushes us at or over the $30,000 mark.
Wow.
So there's a little incentive there.
Leah, if you're here, I have the quilt. I would love to give it to you to take home. So please come find me.
Thank you to everyone who's contributed. Please know that the foundation takes the distribution of those monies very seriously in terms of trying to help us in the teaching and learning of mathematics. Amanda Olson, will you please join me on the stage? Woohoo! Okay, it's not advancing anymore. Oh, now it does. Okay, all right. So I know we're almost through here in Toronto, but we need to start looking forward to Omaha. I'm excited. Amanda.
Hi, everyone. We're kind of at the 7th inning stretch of the conference, so if you want to stand up and kind of just stretch yourself out, next year's theme for the conference is baseball. Omaha is the host site for the College World Series every year, so you can look forward to lots of baseball puns. That's going to be kind of the theme of the conference. I want to talk about some of the best parts of Omaha. One of the great things is that Nebraska is the largest export for beef products, and you can find really excellent steaks just anywhere. I love steak, and it has great steak in Omaha. Another excellent thing is the Capital District. Omaha has a great downtown scene, and I really recommend going there. There's live music, shopping. There's a Jean Leahy Mall, which has a large outdoor slide, kind of like a really giant one that adults can use and stuff like that. You don't have to be a kid. It's kind of like one of those ones that you go to when you're at like a carnival or something that you have to pay to go down. But they have an outdoor one that anyone can just go up and use, and it's really cool. And they just remodeled that. Another great thing is the Bob Carey pedestrian bridge. So there's this bridge. Omaha actually borders the Missouri River, and on the other side of the Missouri River is Iowa, and there's this great light-up bridge that's just beautiful. And when you go onto the bridge, you can actually stand in between Iowa and Nebraska. So if you're trying to if you have a life goal to visit all 50 states, you can actually stand in 2 states at once. And so don't think of just coming to Omaha. You can actually come to Nebraska and Iowa and hit both states. So I really recommend that. And another great thing is the zoo. It's a world-ranked zoo. I am not a zoo person. I didn't think. I was like, okay, a zoo. I'm not really into seeing caged animals. But this zoo is actually really, it's world-ranked. It's one of the best, and it has an indoor safari. And so you can go through, and it's got like a rainforest and like an indoor rainforest, and the animals aren't caged. It's just kind of live, and you can touch stingrays as you walk through, birds and all of that. There's no cages. It's just kind of designed so that the animals aren't really in a caged area. You can just kind of, it's like an interactive experience. It also has a open desert dome, so even though it might be cold, you can still go to the zoo and feel warm. It actually gets kind of hot in the desert dome because it's a desert atmosphere, and so it's really cool. Again, just there's not like a lot of caged animals in there, and it's a really great experience. So if you have kids, I really recommend that. And then the last thing I'll say is that when you guys are in Omaha, when you get there, because you're all going to come, when you get to Omaha, you might kind of see some people kind of like, flagging you down. I want you to know that we're just really friendly, and we're not flagging you down because something's going on. We're actually just waving. And probably from when you get there and when you land, people are going to be inviting you home by the end of it as strangers. That sometimes takes a little bit getting used to, but we absolutely love people, and we're really excited to see you. So please come next year, and as Peyton Manning always says, Omaha, Omaha. I look forward to seeing you guys in 2023. Thank you so much.
Okay, well, this concludes our Saturday morning keynote session. The exhibit hall is now open, so go check out some of our vendors, and I hope you have a wonderful rest of the day.